All right, so you guys have this daily problem, by the way. If you can, please send that to me as soon as possible. You got to work on it. What you had is you wanted to show this function satisfies the Schrodinger equation for a harmonic oscillator. And you had to figure out what conditions you needed on that constant and what is the value of E. So we can start with the Schrodinger equation, which is just h bar psi, and what's that equal to again?
E psi.
E psi.
Yeah, E psi. H bar, you've already, or this Hamiltonian, what's it going to be for a harmonic oscillator? Or H hat, I'm sorry, not H bar. Oh no, I said that. Negative what?
Hopefully h over 2m or h
Yep.
Squared over 2. Okay,
Yep.
did that part right.
And then, because this part's for the kinetic energy, so what else do we need?
Yeah, a second derivative.
Yep. And we'll put psi in there because psi is distributed there. And then what else do we have? We need the potential part. So what is it for like a spring or for the harmonic oscillator?
1/2 k.
Yep, 1/2
squared.
kx squared, yep.
Oh.
And then we got psi. And that's all equal to E psi. So the first thing we're going to look at is we're going to look at that second derivative because we need that part in there. So let's look at the second derivative of psi. Okay. So we got second derivative of e to the negative beta x squared. What's the first derivative of this going to be?
Negative
it'd
2bx.
be 2x. And then the same thing.
Yep. And then the same junk, right? Okay, now if we take the derivative of this guy, we have to follow the product rule, right? So, derivative of the first function, what's that going to be?
Derivative of that would be plus 4
Derivative of this guy.
2b.
Yep.
Or whatever that is.
4b squared x squared e to the same function.
Yep, that's the other one. Good job, Tara.
Okay, doctor.
It's working.
Out of nowhere.
Yeah, I know, out of left field. Okay, cool. So we have this as our second derivative. Now we need to plug this back into our original function. And we get negative h bar squared over 2m, negative 2 beta e to the negative beta x squared plus 4 beta squared x squared, that guy, plus 1/2 squared e to the negative beta x squared. And that's all should be equal to e times e to the negative beta x squared. Whew. Okay. Big long function. Really complicated looking math. Okay, looking at this guy. We got to do something here to make this work out to be an eigenvalue, eigenfunction problem. What terms have to be equal to 0 in order to make this true? In order for this function, this whole side of the equation to look something like this, basically a constant times e to the negative beta x squared. We want these sides to almost be mirrored.
Everywhere that there's our original function and an x.
Probably anywhere there's an x, x might equal 0.
Yep, so this guy and this guy, right?
Yeah.
Yep.
So what we're going to do, we're going to set those equal to 0, and from that we're going to find a beta that will work to make these two portions 0. So we got what is it? Negative h bar 2m times 4 beta squared x squared e to the minus beta x squared plus 1/2. Oh, we forgot a k here, I'm sorry. K x squared e to the minus beta x squared. Like that. And that's all equal to 0. Okay, can we simplify this expression in any way?
Pull out our constant function, like
Yeah.
our original function and the x squared.
Yep, so this guy and this guy, we can pull out, we can move to the other side, which is 0. And what we're left over with, forgot a beta there. So that's all equal to 0. So if we manipulate things around, we just are trying to solve for beta. So let's do that. We get negative h bar squared 2 beta m is equal to negative 1/2 k, right? Then we keep manipulating this, shuffle stuff around. We get to the point where we get beta squared is equal to mk what h2 h bar squared. Actually, that should be a 4. I'm sorry. 4 h bar squared. So what's beta equal to then?
Square root of that.
Got square root of that, where that bottom part, we can pull that bottom part out. We'll worry about that in a little bit, okay? All right, now we need to plug this function back into this equation. The nice part is we know this is equal to 0. That's equal to 0. Hey,
Hi.
how's it going?
Good.
You made it. Cool.
Yeah, I'm on my
Yeah.
phone, so it's like really mini.
Okay, so let's plug in our beta for what we found up here. We really only have to worry about that front function. We get negative 2 square root mk over 4 h bar squared. That square root's meant to go all the way down. Times e to the negative beta x squared, like that. We're going to leave this beta up here because that's just equal to psi. We know we want those two things to go away. So we get our energy is equal to negative h bar squared 2m what else do we got? Negative 2 square root mk. Yeah. Oh, except you can't see it. Yeah. Okay, if you keep manipulating, you keep solving, what you'll eventually find is energy is equal to h bar over 2 square root k over m. Yup.
Is that times negative 2
Yeah.
or minus?
Yeah, that's times. Sorry.
Okay. No, it's okay.
Yep, so it works out that energy is just equal to this constant along here, which works out. So we've proved that this is in fact an eigenfunction. Bless you.
Thank you.
And follows this this harmonic oscillator in the Schrodinger equation. Are there any questions relating to this? I'm guessing the spot where people mixed up, you all probably got to this point, right?
Yeah.
Yeah.
Mhm.
It was just knowing that you saw that there was an x squared there and an x squared here, that those functions aren't going to be eigenfunctions. So you had to set those equal to 0 or find a way to get them to be 0.
So we don't have to fill in like the E part for the B.
Yes, you could.
Over there, yeah.
You could, but the thing is
Doesn't matter.
that should be the same as this guy. So
Gotcha.
these 2 points.
It's not really going to change. Okay.
Yeah, they're the same, so you could just pull them out.
Yeah, it's not.
Cool. Any other questions? Okay, so let's go back to talking about the harmonic oscillator. So last time we reached an energy expression. So let's see. Energy levels. So the next title is energy levels of the harmonic oscillator. We're going to shorten it to HO, so energy levels of HO. Get real ratchet up in here. All right, that's my one joke. Okay, and what did we say the energy expression was for the harmonic oscillator? Energy is equal to what? Came to a pretty simple expression last time.
Is it frequency times age times all of 1/2 plus n?
Yep. Or we organized it a bit different, but yeah, it's that. And what were the values at n that we could have?
Wasn't it 0 and 1?
Yep, 0, 1, 2, and we can keep going, but it starts at 0 in this case. So what does this mean about the, what does this, kind of focus. What does this mean about the energy levels of the harmonic oscillator? Like, how are they spaced? Energy levels of a harmonic oscillator. Which we'll finish the statement in a second. Let's try to draw it out. Fx, E, and these are vibrational energy levels. So if we do n is equal to 0, we have a point that's here. What's that energy equal to for n is equal to 0? E is equal to, using this equation up here. What do we got?
Is this BH?
Yeah, that's 1/2
Or we no,
H.
no.
HV, right? We'll mark that as E sub 0. Next, we have n is equal to 1. What's the value of that going to be?
3 VH over 2
Yep,
and 3/2 VH.
n is equal to 2.
5/2 HV.
Yep. N is equal to 3.
7/2 HV.
Yep. So what do you notice about these energy levels?
It increased by 1.
Yeah, they increase by HV each time, right? So they're evenly spaced. So energy levels of a harmonic oscillator are evenly spaced. And these are actually vibrational motions that we see in infrared radiation or IR spectroscopy. So these go across that way. Okay, so we're going to ask a question. What is the lowest possible energy? For a harmonic oscillator? So we're talking about E sub 0, where we have n is equal to 1/2 h mu. And what's that energy going to be?
Well, n equals 0.
Yep,
So 1/2 HV.
yep, just like we saw last time. So this is the lowest energy that you can get for a harmonic oscillator. And this is what is known as the 0-point energy. So what we're talking about is if we look at a harmonic oscillator, even though this right here is our minimum, the energy that this system has to actually be up here. So this is the 0-point energy. So what does that mean? Oh, ZPE. Label it. So the result is non-zero. So the reason this happens is we're trying to confine a quantum particle. And what do we know happens to the momentum of a particle as we confine it?
Will increase.
Yep, the momentum will increase, right? Hence why the particle keeps moving a lot. So in what principle dictates that?
Oh,
What was that principle? Remember?
Heisenberg uncertainty.
Yeah, yep, it's the Heisenberg uncertainty principle. So that's pretty crazy. If we look at the energy of the system, we try to confine it to a potential, and what happens is the uncertainty principle kicks in. And for our purposes and for like practical purposes, when we consider any quantum system, any molecule, it's usually found in its first vibrational state where n is equal to 0. It's just moving a little bit, but it's not moving a ton, hopefully. Okay, so now let's look at the wave functions. We found an energy for a harmonic oscillator, and we've seen we've seen like a trial or a practice function in that daily problem. Let's get to the harmonic oscillator wave functions. Okay. So what do we know about the wave function so far? So if we look back to what we did, I think on Friday or on Monday, what did we see for that wave function? How do we start to define it before we got to that energy expression? Anybody remember? I know lots happened since then. So we got to a point where we were looking at derivatives. I think we had e. You remember any more beyond that? E to the negative alpha.
Negative alpha x squared over 2 times f of x.
Yeah, x squared over 2 divided by 2 times what else was there?
The power series?
Yeah, the power series, f of x. And that, remember, was a power series. Okay. And do you remember what this power series depended on? Not only does it depend on x, but it also depends on another thing.
See?
Yep, well, the c's are the results. It was based upon that n value. So f of x for an even n is given by this series. X of n, and this was for even, goes to infinity, and we have f of x of odd is equal to n is equal to 1, infinity odd Tn x sub n. Now these two things look almost exactly alike, but they're a little bit different because remember we had to separate out all the even functions and all the odd functions or odd values for that recursion relation, or else we would get an infinite value when it came to our wave function. So let's look at the wave functions for the first couple of energy levels. We're going to get that e to the negative alpha x squared over 2 times. What are we going to get? Remember, 0 is considered even in this case. What else do we need to include for our power series? So if we have n is equal to 0, what's this become?
It becomes C of n.
Yep, c of n or c sub 0. Okay. Psi 1. We still get that exponent part. Times, what are we going to get in that case? Remember, this is an odd one. So if n is equal to 1, what do we get?
C1x.
Yep, c1 x to the power of 1 psi 2, that same exponent part. In this case, this is an even function, right? So what's going to be in this bracket?
C0 plus
Yep.
C1x1.
Not
Or no, we're just doing evens. So
Yep.
then it'll be C2x squared.
Yep, exactly. Psi 3,
It'll be C1x1 plus C3x cubed.
yep, exactly. So does it make sense for people?
Times x.
I'm sorry, what was that?
Would that be C1 times x? Or just
Yes, I'm sorry, there should be an x there, my bad. Is that making sense to people? So see how to tell if it's even or odd, you look at that index, and then you use this to try and determine that. Make sense?
Yeah.
Okay. Cool. Okay, but now the problem is we haven't normalized these things, so we have to normalize their functions. We need to normalize these functions to get the constants. And what we're going to do, we're actually going to group these constants into the normalization constant. Into normalization constants. Okay. So let's look at the first one. So what is the normalized psi naught or a harmonic oscillator? Okay. So we're trying to normalize a wave function. What do we have to do to normalize a wave function again?
Integrate over 0 to a,
Yep.
multiplying by its complex, not complex, I mean conjugate.
So that guy, and what's that all equal to?
1.
0 or 1.
Yep, that's equal to
0.
Oh.
0.
In this case, we didn't set bounds for our function. It can be anything, right? It just has to follow that potential. So we're going to go from negative infinity to positive infinity. So if we do that, we have an n squared out front, right? That's our normalization constant. Negative infinity, positive infinity. Now, what is our sine knot that we had? If we look back up here, what we just had this, right? And we're going to group this constant into the normalization constant. So we should just get the complex conjugate of that function. Does anything change with the complex conjugate of this guy?
No, because there's no I.
Yep, no I, so we stay the same. Times e to the negative alpha x squared over 2 dx. Okay. So we're still going to get our n squared out front. We still have our integration. What happens to this as we multiply those two things together?
This becomes a 2 out front, canceling the half.
Yep, the halves cancel out, so we should get e to the minus alpha x squared dx. Okay.
Or wait, oh, that's okay. That's an alpha. Never mind. I thought that was a 2.
Okay, now we're going to use a little trick. So since x squared will result in a positive value, what can we do? How can we simplify this?
Take the negative. Or wait.
It has something to deal with our integration limits.
Yeah. So just 0 to positive infinity.
Yeah. And what do we have to do
Minus
to
2.
this function then? We got to multiply this by some scalar, right?
Yeah, it should be 2.
Yep. Since we're going to a positive value, we know that f of negative x is equal to f of x, right? That means if we only go from 0 to infinity, then we can easily just multiply that by 2. Okay, so now we are left over with this as a function. So we'll go to a new page. Okay, so now we have n squared times 2 integral 0 to infinity e to the minus alpha squared. All right, what are we going to do with this guy? Anybody know how to integrate that?
Some u substitution and see how it goes.
Yeah, you could do that. I'm lazy. What we're going to do, we're going to look up from a table of integrals.
Can you move that paper just down 1 second so I could get that last line?
That's it?
Yes, please. Okay, thank you.
All right. So now we got table of integrals. Integral. What do we got? E to the minus alpha x squared. Actually, we'll do a to make it a little more formal. Dx 0 to infinity is equal to 1/2 pi over a to the 1/2. Sorry, making things fuzzy.
So
Alpha.
that negative is actually part of the integration.
Yes.
So when we plug in our function, would that negative go away, or is that like saying that it's there? So
just
equal that.
that's just saying it's there. So what are we going to get for this guy up here? We're still going to get that 2n squared times what?
1/2 times pi over alpha to the 1/2.
Yep, exactly. Okay, now we know what this is all equal to. What's that equal to? Like the value that we set up in the beginning?
1.
Yeah, 1. Now we have to solve for that n. As we manipulate everything through, what you'll find is n is equal to alpha over pi raised to the 1/4. So therefore, what is our normalized wave function for size 0?
Square root of all that.
Not quite. What was our original function? E to the what?
E to the negative alpha x squared over 2.
Yep. And now we have to plunk in that normalization constant. Oh shoot, I'm sorry. This is equal to n.
Yeah.
That's why. You were right, Maddie. What I told you. I'm sorry.
I always am.
It's hard always being right, you know.
I know.
Okay. So that was for the simple case. What we can do is we can show, we're not going to completely, it can be shown for the harmonic oscillator. The wave function follows a certain pattern, which is beneficial. Certain pattern. And it can be expressed as the following, where we have psi sub n is equal to alpha over pi raised to the 1/4 times 1 divided by 2 to the n times n factorial 1/2 h sub n x times e to the negative alpha squared. Okay, where this guy is known as a Hermite polynomial. And we'll talk about that in just a moment. Okay, everybody remember what factorial means? Like if I have 3 factorial, what does that mean?
3 plus 2 plus 1.
Not plus.
3 times 2 times 1.
Yep. What is the one with pluses?
The summation.
Oh,
Sigma.
okay. There we go.
Yeah,
Okay. Sometimes though, this looking at the Hermite polynomial for that can be complicated. So for convenience. Oh, except I'm misspelling that. I don't know if that's any better. We can express this Hermite polynomial rather than this. We can represent it as a single variable. We're going to give it this crazy e epsilon, where epsilon, oh, except I'm screwing it up on that was terrible. It's defined as alpha x that way. And I'll show you why that's beneficial in a moment.
How is that? What is that symbol?
It's meant to be an epsilon. The better way, like a capital epsilon. Like remember when we did extent of reactions in PChem1
Yeah.
thermodynamics? It's meant to be that symbol. Yeah.
Like the E with a loop.
Yeah. Loopy E. Okay. And now these Hermite polynomials, they come from mathematics. And they're solutions basically to a differential equation, the differential equation that we have. And they satisfy a recursion relation. The important point is we can talk about those more in depth if people want to, but I want to get to their result more so because that's more beneficial for us. So N, we're going to keep track of the index. That's going to be N on each. And we're going to have what the Hermite polynomial looks like. 0, 1, 2, 3, and 4. And these, you can look them up. They can be found in your book. The benefit is that n is equal to 0. This Hermite polynomial is equal to 1. For an index equal to 2, we get 2 epsilon. For 4, or for 2, we get 4 epsilon minus 2. 3, we get 8 epsilon raised to the power of 3 minus 12 epsilon. For 4, we get 16 epsilon 4 minus 48 epsilon squared plus 12. And you can look these up. They're all in your book to see. Okay? Let me check something real quick. For your daily problem, you're going to be using some of this information. Let's do one example and then we'll call it quits for today. Does that sound good to everybody?
Sure.
Okay. Am I okay to move this?
Yeah.
Okay. So now, as an example, let's normalize psi1 for a quantum harmonic oscillator, quantum Ho. Remember normalization, like we said, is basically looking across our integration limits and solving for that normalization constant. Okay. Psi1 of x, if we go back to,
I can't really see it that well.
oh, okay, sorry, it's spasm, we'll throw that down. So we showed, or we talked about how we can use this expression to solve, to write out our wave function. So we're going to use that to write out our psi1. So we're going to keep that alpha pi raised to the 1/4. What does this term become if n is equal to 1?
The 1/2.
1/1/2 to the 1/2, right?
Yeah.
H1 x e to the minus alpha x squared. Okay, so we have to look up this guy. We'll do that in a moment. Okay? So for now, let's take this and plug it into our expression up here. So integral would go from negative infinity to positive infinity. We're going to have n squared what else do we got? Oh, I'm sorry. We want to ignore this part for now. That's part of the normalization constant. so I gave that away. But we want to try and find that. We want to show that that's true.
So are we using those harmonic oscillator wave functions that we did with like the even and odd?
Yes, they are. The even and odd are the result, like the result that you get comes from this guy. You could look at that even and odd, like we could look back at this guy if we wanted to, but an easier way to do it is actually to go through these Hermite polynomials. It doesn't look it right now, but I promise you it is. So we know that this is what our result is going to be, but we're going to pretend we don't know that yet. Okay, so we have n squared times h1 x star e to the minus alpha x over 2 times h1 x e to the minus dx. Did that answer your question, Josh?
Yeah.
Okay.
Are you playing Uno?
Really not yet.
All right. Now we want to sub, if we look back at this table, we have everything in terms of epsilons. So we want to sub in that epsilon into this equation. And d epsilon into equation. And remember, we defined epsilon as alpha to the 1/2 times x. So let's sub that into here. When we do that, we get n squared, negative infinity, positive infinity, h1 epsilon star e to the minus epsilon squared over 2 times h1 epsilon e to the negative epsilon. Yes. Sorry. One-half. All right. So we can manipulate that around, and what we get is the n squared over alpha, the 1/2 h1 epsilon e to the negative epsilon squared, which is all equal to 1. Oh, except we need a d epsilon.
So why is d epsilon divided by alpha 1/2 at the end of the second of that line?
So we said that this is equal to one another.
Yeah.
If we do d epsilon, geez, I'm terrible at that. D 1/2 dx. What is dx going to be equal to?
Oh, I guess, okay, d divided, all right.
Mm-hmm.
Fair enough.
There we go. That's where that comes from. All right, I promise you we're almost done. So the nice thing is Hermite polynomials, they have really simple integrals due to orthogonality. So Hermite polynomials have simple integrals due to orthogonality. So as an example, we have a first Hermite polynomial times a second Hermite polynomial, and this epsilon squared we're going to get two results. We get 0 and we get 2 to the a factorial pi to the 1/2. Remember what orthogonality means? So if we get 0, what does that mean? What has to be true about this function?
Equals 0?
Yep, for it to be 0.
Oh, 4, 3, 0?
Mhm.
Isn't it like I can't equal J, so A can't equal B or something like that?
Right. If A does not equal B, that's going to be 0. If A equals B, and they're the same Hermite polynomial, you get this as an integral. So now, if we plug that back in to our previous expression, well, let's just look at it for alpha 1. H1 epsilon times H1 epsilon e to the minus epsilon squared epsilon. So if we take that integral, what is our value of A in this case? So remember, A is down here,
That's 1.
1. So what's the resulting integral going to be? 2 to the 1, 1 factorial, pi to the 1/2. So what's that equal?
2 pi to the 1/2.
Yep. Okay, so let's plug that back in. We know that out front, when we were back at this point, that whole integral that we have, it would be equal to n squared alpha to the 1/2 times this guy. So we're 2 pi to the 1/2. And that's all equal to 1. If we manipulate that through, what we'll see is n is equal to alpha over 4 pi to the 1/4. And this matches our generic equation. The one that we determined, oops, sorry, I'm moving stuff on you. The one that we determined with this guy. So it matches. Okay, sorry, I went over time, but I wanted to get through that because that can help you guys on your daily problem quite a bit. I knew we flew through some of the mathematics, but does anybody have any questions at the moment?
So this is what we're doing on our daily problem?
Not
Yes.
currently.
Yep, you're going to do this exact same process, except for n is equal to 2 in that case.
That goes.
Okay?
Okay, how